Before the end of World War II, German engineers had built things that the world would take decades to understand. From Peenemünde, Werner von Braun launched the V2, a projectile that fell on London at supersonic speed, invisible until impact, and whose principles would eventually guide the Sputnik 1 launch and, shortly after, humans to the moon. The Me-262 flew through formations of Allied bombers at a speed no gunner could follow, while the Jagdpanther destroyed 3 Shermans in 40 seconds from positions that no one could locate, with a cannon capable of piercing Soviet armor from 2 kilometers away. These achievements were not just the result of isolated technical innovations. Behind them was a sophisticated coordination system. The Sd.Kfz 251 revolutionized the battlefield with an advanced system of 3 radios operating simultaneously, allowing Erwin Rommel to command entire divisions under intense enemy fire. The Blitzkrieg was not just speed and tanks, it was above all a revolution in communications. This documentary exposes the 17 most advanced and influential Nazi vehicles of World War II. Me-262, how Hitler got the best fighter in the world. On July 18, 1944, Lieutenant Richard Lerner of the 8th U.S. Air Force wrote a combat report with a sentence that intelligence analysts in Bushy Park underlined before passing it to their superiors. It described a craft that crossed the B-17 formation at a speed that no gunner had been able to follow with their turrets. There was no time to react. The object simply existed and then disappeared. The origin of the Me-262 wasn't in 1944, but in January 1939, when the Messerschmitt Company received a specification from the Reich Ministry of Aviation for an experimental jet fighter. Engineers Josef Waldemar Voigt and Ludwig Bölkow led the design of the airframe, the structure of the aircraft itself, while the engines were developed in parallel at Junkers under the direction of Anselm Franz. The problem was that the engines required materials that Germany could not obtain. The turbine blades of the Jumo 004, the parts that spun inside the engine at 800 degrees Celsius, required nickel and chrome alloys. The Allied blockade had turned those metals into a permanent scarcity. Franz found an engineering solution, an air-film cooling system that cooled the blades using internal currents and allowed the use of inferior materials. It worked, but at a cost. Each engine lasted only 25 hours before needing a complete overhaul. Every Me-262 in active service consumed 2 engine overhauls for every 50 hours of flight. That was the technical problem. The political problem was even more devastating. On May 23, 1943, in Berchtesgaden, Hitler questioned General Erhard Milch about whether the Me-262 could carry bombs. Milch answered yes, without anticipating what would come next. Hitler, who had become obsessed with the idea of a high-speed bomber that could destroy Allied beachheads before they could be consolidated since the failure to contain the Normandy landings in June 1944, ordered the Me-262 to be converted into what he called a blitz bomber, a lightning bomber. The decision was technically absurd on 3 different levels. The aircraft had no bombing sighting system. Its engines responded dangerously slowly to power changes during evasive maneuvers, making each sortie an added risk. And the bomb load reduced its speed advantage to nearly nothing, the only reason for the aircraft's existence in combat. General Adolf Galland, the Luftwaffe's Inspector General for fighters, directly confronted both Göring and then Hitler. He explained all of this with the data in hand. He was told, without much tact, that his objections would not be considered. The months that followed, from mid-1943 to the end of 1944, were lost in forced conversions, failed tests, and technical reversals. Those months represented the difference between a weapon that could have altered the air balance over central Germany and one that came when the balance was already irreversible. When Jagdgeschwader 7, under the command of Major Theodor Weissenberger, began interception operations in November 1944, the combat results confirmed everything Galland had argued. The JG-7 destroyed over 400 confirmed Allied aircraft. The elite unit, Jagdverband 44, which Galland himself finally managed to organize with the best available pilots and which entered combat in February 1945, accumulated victories at a rate that no conventional combat unit could match. But facing the 9,000 Allied aircraft operating over Germany in those final months, even 300 operational Me-262s at their best could not reverse the tide. The margin of tactical superiority was real. The scale of the strategic imbalance was greater. Meanwhile, the Allies did not wait passively. General Karl Spaatz, commander of the strategic air forces in Europe, authorized specific patrols over the German airfields where the Me-262 was operating in October 1944. The pilots learned two specific vulnerabilities of the new aircraft. First, the turbojet engines required several seconds of startup before responding with full power, a combustion threshold that made the Me-262 slow and predictable in the first few meters of takeoff. Second, during takeoff and landing, with engines at minimum power and the aircraft 200 meters from the ground, it was as vulnerable as any other. Lieutenant Colonel James Selman of the 357th Fighter Group shot down the first confirmed Me-262 in a low pass over the Lechfeld runway on August 26, 1944, attacking the aircraft as it touched down. Then came the systematic tactic, not intercepting in flight, where it was impossible to catch, but at the moment of greatest vulnerability, in the seconds of takeoff and landing. Of the 1,433 units produced, including the Schwalbe fighter, the Sturmvogel bomber, the Nachtjäger night fighter, and a twin-engine reconnaissance variant, fewer than 300 were operational at any one time. J-2 fuel was scarce, pilots trained in turbojets even more so. The runways were a permanent target for Allied aviation. Everything conspired against the scale that would have made the difference. By the end of the war, Allied technical intelligence teams, the British T-Force and the USA AF teams competed urgently for the captured specimens. What they found in the German hangars directly informed the development of the North American F-86 Sabre and the Soviet MiG-15, the two fighters that would fight over Korea 5 years later. The delta wings of the Me-262 and the principles of the Jumo 004 became the foundations of post-war military aviation. The Me-262 did not win the war for Germany, but it defined the technical terms of the next one. Why Germany built the best tank destroyer of the war in 1944? At 11:34 on August 2, 1944, the radar sergeant at the Chain Home Station in Pevensey on the Sussex coast recorded an unusual contact. Estimated speed, 740 kilometers per hour. Altitude, 9,000 meters. Heading inland towards England. He alerted the Fighter Command Operations Room, and within the next 14 minutes, 3 Spitfire Mark 14S, the fastest fighters in active service with the RAF, were vectored towards the contact. None could get within 2 kilometers of the target. The intruder turned over Southampton and returned to the continent without being intercepted. The sergeant's report concluded with a sentence that the command underlined before passing it to intelligence. The target maintained a constant speed advantage in all interception attempts. The Arado R-234 was the materialization of an idea the Luftwaffe had pursued since 1940, a reconnaissance aircraft that operated faster than any enemy interceptor. Walter Blum's design team at Arado Flugzeugwerke in Brandenburg an der Havel received the original specification in April of that year and responded with a design of remarkable aerodynamic purity for the time. The fuselage was a nearly circular tube, with a glazed cockpit in the nose that gave the pilot panoramic visibility in all directions. 2 Junkers Jumo 004B engines hung beneath thin wings. There was no defensive armament. Speed was the only defense, and given the aircraft's performance, it proved sufficient. The first prototypes used a takeoff system that was abandoned on the runway, while landing was done on 3 retractable skids beneath the fuselage. This solution eliminated the weight of conventional landing gear, but created an insurmountable operational problem. The aircraft became immobilized after landing, unable to move by its own power to the takeoff runway. In bases with several aircraft operating in rotation, this caused bottlenecks that made any sustained operational rhythm unfeasible. The V5 to V8 prototypes adopted the standard retractable tricycle landing gear, with which the AR-234 finally went into production as the B model. The Versuchsverband OB-DL, an experimental unit under direct control of the Luftwaffe High Command, received the first operational R-234B1 aircraft in July 1944. The reconnaissance flights that followed covered the ports of the English Channel, Allied installations in Normandy and communication lines in France. The photographs arrived at the German intelligence centers with a regularity that no Allied defense system could interrupt. RAF intelligence photo interpreters who analyzed the captured images knew exactly what this meant. Germany could still see precisely everything the Allies were doing on the ground, and there was no way to prevent it while that aircraft existed. The attempts to intercept the R-234 over Britain and the Netherlands during the fall of 1944 generated dozens of alarms and 0 confirmed shoot-downs. The bombing variant, the AR-234B2, added a new dimension to the problem. The bombing system used a Lotfe 7K sight assisted by an autopilot. On the approach to the target, the pilot activated the autopilot, which maintained heading and altitude steadily and physically moved toward the site located in the aircraft's nose. From there, the pilot calculated the firing solution, activated the release, and regained manual control before initiating the evasive maneuver. It was a procedure that required practice and considerable composure under anti-aircraft fire, but in the hands of trained pilots, it provided reasonable accuracy for an aircraft that no enemy interceptor could reach. The most dramatic episode of the R-234 in combat was the campaign against the Remagen Bridge in March 1945. On March 7th, the 9th Armored Division of the US Army captured the Ludendorff Bridge over the Rhine before German engineers could blow it up. It was a disaster for the German command. The only intact Rhine crossing could become a bridgehead that would open the way into the heart of the Reich without natural obstacles. R-234B-2 units of 3/Kg-76 carried out bombing missions against the structure. The Allied anti-aircraft concentration in the area was the densest on the entire Western Front. Hundreds of pieces of all calibers permanently protected the crossing. The R-234s repeatedly flew over it, dropping 500-kilogram bombs that damaged the structure but did not destroy it. The bridge collapsed on March 17th, 10 days after its capture, due to its own accumulated structural stresses. The AR-234 attacks had shown that it could operate in the densest defensive environment on the front. They had not shown that it could compensate for the shortage of heavy precision munitions available to Germany in its last months of war. The 210 units produced were studied in detail by Allied technical teams who captured specimens at the Norwegian base of Stavanger and at German airfields in the north. Its design principles, the clean aerodynamics, the placement of the engines under the wings, and the cockpit integrated into the nose, influenced the jet bomber programs of several countries in the following decade. Bf-109, the fighter that combated from Spain in 1937 to Berlin in 1945. On November 5, 1942, over the Caucasus, a 20-year-old pilot named Erich Hartmann shot down his first Soviet aircraft. He was flying a Bf-109G. The tactic he used that day was the same he would use in the next 351 confirmed victories, all of them in the same basic type of aircraft, making him the fighter pilot with the most confirmed kills in military history. The tactic was simple in description, but extremely difficult in execution. Approach from the adversary's rear and upper blind spot, close to a distance where it was impossible to miss, a burst of less than 2 seconds, and an escape maneuver before the target could react. Hartmann said that one had to see the target fill the sight completely before firing. The Bf-109, in the G and K versions he flew throughout his career, provided what the tactic required: speed superior to that of his adversaries, concentrated armament in the nose with precise convergence at the aiming point, and enough flight stability to execute the burst under control. The Bf-109 was designed by Willy Messerschmitt and his team in response to the RLM 702 technical specification of 1934, which called for a modern fighter to replace the Heinkel HE-51 biplane with which the newly reconstituted Luftwaffe operated. The design philosophy was radical for the standards of German military aviation at the time: the minimum possible weight and the maximum utilization of engine power. The fuselage was of minimal section, just enough to accommodate the pilot, the engine, and the fuel. The wing was small, which required highly efficient flaps to maintain manageable approach speeds on the ground and produced slow flight behavior that pilots had to learn to manage. The Jumo 210 engine of the prototypes was replaced by the Daimler-Benz DB 601 engine in the E version, the Emil, which entered combat with the Condor Legion in Spain in 1938 and then in the Polish campaign in September 1939. The Battle of Britain in the summer of 1940 simultaneously showed both the virtues and the limits of the aircraft. The direct fuel injection of the DB601 provided a concrete and repeatable tactical advantage. In negative dive maneuvers, when the aircraft forcefully pushes the nose downward, the Bf-109E's engine continued running without interruption, while the British Spitfires and Hurricanes, with conventional carburetors, lost power during a few critical seconds. The German pilot could escape with a simple push of the nose forward, which the English could not immediately follow. It was a design difference that in real combat made the difference between escaping and being shot down. But the Bf-109E's range was only 660 kilometers, insufficient to provide prolonged escort for the HE-111 and DO-17 bombers over southern England. The Bf-109 reached the English coast with limited time before it had to return for fuel, and pilots were constantly aware of the counter running against them. Forced to stay close to the bombers instead of seeking free combat in the conditions that favored them, they systematically wasted the main tactical advantage of their aircraft. The Bf-109F, introduced in 1941, was the version that many veteran pilots considered the most balanced of the entire series. With a deep aerodynamic overhaul and the improved DB601E engine, the Friedrich reached 623 km per hour and combined speed, agility and firepower in a proportion that those pilots consistently described as perfect. The G version, the Gustav, was the most produced, with over 24,000 units built. To compensate for the improvements of adversaries, it incorporated the GM1 nitrous oxide injector to maintain performance at altitudes above 8,000 meters. The MW50 water methanol injection system, which provided extra power during the critical moments of combat, added weight and complexity to every improvement, and the Gustav inherited and amplified the original design flaw that cost the Luftwaffe the most, lives starting in 1943. The Bf-109's landing gear had a track of only 2.05 meters, the distance between the two wheels on the ground, with a pronounced canting angle that made the aircraft unstable during takeoff and landing. It was an aircraft that forgave little to inexperienced pilots, and from 1943 onward, the German fighter squadrons were filled with young pilots, with drastically shortened training programs to compensate for the losses at the front. The combination was routinely fatal. The instructors at the Jagdpanther, the fighter schools, documented with growing alarm the takeoff and landing accidents that rendered aircraft and pilots unfit for action, who never even got to see the enemy. The only German fighter that surprised the Allies from 1941 to the end. In October 1943, Lieutenant Don Gentile of the 336th Fighter Squadron of the USAAF, one of the most decorated American aces on the European front, wrote a direct evaluation of the FW-190 for the Tactical Manual of the 8th Air Force. The central sentence was this: when a FW-190 decides to attack and has the position, there is no maneuver that can stop it. You have to avoid the position from the start. It was the unembellished recognition that Germany had built an aircraft in 1941 that 2 years later remained one of the most dangerous in European skies. The first appearance of the FW-190 over the Western Front in September 1941 produced an effect that few technological innovations achieve in war: complete strategic surprise. The RAF, with the Spitfire Mark V as its main frontline aircraft, had nothing at that time that could match the new German fighter in horizontal speed, dive speed, roll rate, the speed at which the aircraft can bank to turn, or firepower. British fighter commanders sent urgent reports to the Air Ministry. The response was that the RAF could not match the FW-190 until the Spitfire Mark IX with the Merlin 61 engine was available in quantity, and that would take almost a year. During that year, the FW-190 dominated the skies over the Channel with a hegemony that official reports euphemistically described as showing significant losses for British squadrons. Kurt Tank, the chief designer at Focke-Wulf, had made a decision that set him apart from all other German fighter designers. He chose the BMW 801 radial engine when the general trend preferred inline engines, which were sleeker and had less aerodynamic drag. The choice was deliberate and defended with concrete arguments. Radial engines were more resistant to combat damage because their cylinders, arranged in a circle around the crankshaft, could lose some and still keep running. They were easier to maintain in the field because they didn't require the liquid cooling system with its pipes and radiators, which made the Bf-109 vulnerable to minor damage. and they were more powerful in absolute terms once the BMW 801 reached maturity. The initial model, the FW190A1, with the BMW 801C engine of 1,560 horsepower, reached 626 km per hour. The FW190A3, with the BMW 801D2 engine of 1,700 horsepower, reached 654 km per hour at 6,300 meters of altitude. The management of the engine was the great ergonomic innovation of the FW190, and its implications for the pilot in combat were immediate. An electromechanical device called the Kommandogerät automatically adjusted the fuel mixture, turbocharger pressure, and propeller blade pitch based on the throttle position. The pilot moved the throttle lever, and the system did the rest. In a combat where Bf 109 pilots had to manage multiple technical parameters simultaneously under extreme pressure, FW190 pilots could concentrate solely on flight tactics. Tank had designed a pilot-machine relationship that post-war aviation ergonomics would take years to match systematically. Armament was the other main differentiator. The A8 variant, the most produced of the series with more than 6,500 units built, mounted four 20mm MG 151/20 cannons, two 7.92mm machine guns in the nose, and two additional 20mm cannons under the outer wings, 6 barrels in total. Against a B-17 Flying Fortress, this rate of fire was devastating. The Jagdwaffe, the German fighter force, determined that 3 seconds of concentrated fire with the A8's full armament were enough to destroy a B-17 with high probability. The FW190 became the main tool of the Reich's defense against USAAF bombing raids, with pilots of specialized Sturmgruppen units being ordered tactically to close within 200 meters before firing, a range at which impact was nearly certain and the attacker's survival was not guaranteed. The D9 variant, the Dora 9, introduced in August 1944, was Kurt Tank's technical response to the Spitfire 14 and the P-51D Mustang, which by then had matched and, in some aspects, surpassed the FW190A at high altitudes. Tank replaced the BMW 801 with the Jumo 213A, a 12-cylinder V-engine cooled by liquid, returning the aircraft to the advantage it had lost. The Dora reached 686 km per hour at 6,600 meters. German pilots who flew it consistently described it as the best German propeller fighter of the entire war. Adolf Galland, after flying a Dora 9 in January 1945, stated that they finally had something to fight on equal terms against their Allied adversaries. The problem was the same as always in those final months. There were not enough Dora 9s, not enough fuel, and not enough trained pilots to exploit it. Approximately 20,000 FW190s were produced in all its variants between 1940 and 1945. The Soviets captured examples during operations in 1944 and 1945, analyzed them in detail, and some principles of the automatic mixture control and the high-performance radial engine influenced the development of Soviet fighters in the final phase of the war and the immediate post-war years. The FW190 was the only German fighter of the entire war that maintained the ability to surprise the Allies from its appearance in 1941 until its last day of combat. Warsaw in trouble, how 18 Sturmtigers destroyed the Polish resistance. Captain Helmuth Welz, an infantry officer in the 14th German Regiment at Stalingrad, described in his 1959 memoirs what he called the war within the war. Every building was a position, every staircase a battlefield, every basement a fortress that had to be taken room by room with grenades and pistols. Conventional artillery was useless because the buildings absorbed direct hits with an inertia that the 75mm shells barely disturbed. What was needed, Welz wrote, was something that could turn a building to dust with a single blow. The Sturmtiger was exactly that. Developed from the lessons of Stalingrad and urban combat in Sicily in 1943, the Sturmmörserwagen 606/4 answered a specific question posed by street fighting that had gone unanswered: how to destroy heavily entrenched enemy positions in masonry structures without exposing infantry to sniper fire and without relying on field artillery, which required fixed positions, slow response times, and was vulnerable to front movements. The Alket Company developed the vehicle throughout 1943 on the modified chassis of the Tiger I. The engine was moved to the center of the vehicle to create space for the weapon's loading system. That weapon was the RW61, a 380mm adaptation of the Kriegsmarine's anti-submarine rocket launcher, which the Navy had developed to launch depth charges against submarines. The rocket shell weighed 330 kilograms, of which 125 were high explosive. A direct impact on a 4-story masonry building was, according to tests conducted in Hillesleben in June 1943, equivalent to the simultaneous detonation of 300 hand grenades. The pressure wave collapsed adjacent structures that had not received the direct hit. The crater in open ground measured between 4 and 5 meters deep and 10 meters in diameter. Handling a 330-kilogram shell within an armored vehicle was an engineering problem that the design of the Sturmtiger solved elegantly. A 2.5-ton crane mounted on the rear deck, hydraulically operated from inside, transferred the shells from external supply vehicles into the chamber without exposing the crew to external fire. Inside the vehicle, a rail-mounted loading trolley moved the shell from storage racks to the chamber. The entire loading process took about 10 minutes, which set the maximum fire rate at around 6 shots per hour under ideal conditions. It was not a continuous suppression weapon. It was a high-precision demolisher with slow reloading and a definitive effect. The superstructure had 150mm frontal armor. The total weight reached 65 tons. The firing arc of the RW61 was narrow, from 0 to 85 degrees of elevation and 10 degrees on either side of the vehicle's centerline. For targets outside this arc, the entire Sturmtiger had to be moved, which in urban combat among rubble, destroyed vehicles and narrow streets was a real operational limitation that the crew managed by coordinating with the infantry accompanying them. The first operational deployment was during the crushing of the Warsaw Uprising in August and September of 1944. The Polish Armia Krajowa had turned Warsaw into a network of defensive positions with tunnels under the sewers, snipers in bell towers, and machine gun nests at every intersection. The Sturmtigers of the 1st Sturmmörser Company were employed to systematically demolish the blocks of buildings with the greatest resistance. The tactical effect was decisive. There was no position that could withstand a direct hit from the RW61. The cost for the Polish civilian population trapped in the surrounding buildings was catastrophic. Reports from SS General Erich von Dembach-Zelewski, who commanded the operation, cited the Sturmtiger as the most effective weapon for neutralizing the strongest urban resistance points. Only 18 Sturmtigers were produced, built at the Alket factory in Berlin-Spandau from Tiger I chassis recovered from combat and repaired. The low number reflects both the limitations of German industry in 1944 and the recognition that it was a weapon specialized for a type of combat that Germany hoped it would never need: urban combat on home territory. The fact that it was ultimately used in the defense of German cities against the Allied advance in 1945 was, in itself, the clearest indication of how much the war had changed. How the Soviet T-34 redesigned the Panther, the tank the Allies feared the most. In October 1941, somewhere between Bryansk and Orel, a column from the 4th German Panzer Group encountered a concentration of Soviet T-34s that didn't retreat. The Panzer III fired at 600 meters. The shells bounced off the T-34's sloped armor. The 50mm gun of the Panzer III, perfectly effective against earlier Soviet armor, lacked the penetration power against the geometry that the engineers in Kharkov had incorporated into the T-34. The sloped armor wasn't just thicker, the angle made the shells tend to deflect rather than penetrate, multiplying the actual protection beyond what the nominal thickness suggested. General Heinz Guderian toured the front in November 1941 and described the experience in his report to the OKH in unambiguous terms. "The Russians have a tank that we cannot match with current means." The Special Tank Commission that the OKH sent to the front in November 1941 arrived with engineers from MAN, Daimler-Benz and Henschel, with the explicit task of analyzing the T-34 and recommending how to copy or surpass it. The debate that followed revealed internal tensions in the German armament program that would have consequences for the rest of the war. Daimler-Benz's team proposed a functional copy of the T-34 with specific improvements in optics and communications, a diesel engine, sloped armor, and suspension adapted from the Christie design. It was quick to implement. The Ministry of Armaments, first under Todt and then under Albert Speer, initially favored this solution for exactly that reason. Hitler, who personally supervised the armored developments with micromanagement that frustrated generals, preferred the MAN proposal, not an improved copy, but a vehicle that incorporated the lessons of the T-34 and then surpassed them in firepower and protection. The result was the Panzer V Panther. It incorporated 55-degree sloped armor on the front of the hull and turret, surpassing the T-34's protection. It surpassed it in firepower with the KWK 42-75mm L70 gun, a weapon whose L70 designation indicates that the barrel length is 70 times its caliber, which results in higher projectile speed and therefore greater armor penetration. And it exceeded it in optics with a Zeiss TZF-12A binocular sight, which allowed targets to be identified and engaged at distances where the T-34 still fired by the commander's visual estimation. Production began in November 1942 at the MAN plant in Nuremberg, with additional production spread across Daimler-Benz, Henschel, and other facilities. The baptism of fire at Kursk, Operation Citadel on July 5, 1943, was a technical disaster. Of the 200 Panthers deployed in the southern sector of the 48th Panzer Corps, about half experienced severe mechanical failures within the first 48 hours. The Maybach HL-230 engine overheated. The ZFAK 7-200 transmission, designed to transmit 700 horsepower through a chassis that now weighed 44 tons, failed under the strain of the nighttime movements to the starting positions. Fires in the engine compartment, caused by defective fuel connections in the early production batches, rendered dozens of vehicles useless without firing a single shot. It was the worst debut of a German armored vehicle in the entire war. What followed was notable for its speed. Field engineers identified the defective fuel connections in the first week of combat. Speer dispatched technical teams directly to the front. Modifications were incorporated into the production line. By the fall of 1943, the Panther Ausf. A was significantly more reliable than the Ausf D that had fought at Kursk, and the Ausf G, introduced in March 1944, was the mechanically most robust version of the entire series. The nearly 6,000 Panthers produced in total fought on all European fronts, from the Ukrainian steppes to Normandy and the Ardennes. The Allied commanders who faced the Panther feared it more than the Tiger I, the most publicly famous German heavy tank. The M4 Sherman, the workhorse of the US Army and its allies, could not penetrate the Panther's frontal armor at normal combat distances with the standard 75mm gun. The 76mm gun introduced in the M4A3 76W variant could achieve this at less than 400 meters, a distance at which the Sherman crew rarely survived long enough to fire. General Omar Bradley acknowledged in his memoirs that this asymmetry was compensated by the numerical superiority of the Allies, but it was not solved. The Soviets, who captured Panthers in large numbers during the major offensives of 1944 and 1945, analyzed them in detail, and some principles of their design directly influenced the T-54, the tank that would define Soviet armored doctrine in the post-war years for decades. 3 Shermans destroyed in 40 seconds, the Jagdpanther that no one could locate. On the first day of the Ardennes offensive, December 16, 1944, in the northern sector of the attack, 3 Sherman tanks from the US 743rd Tank Battalion were destroyed in less than 40 seconds. None of their crews were able to identify the aggressor. The Jagdpanther, which opened fire from the edge of the forest at 1,400 meters, fired 3 times with 11 seconds between each detonation. Post-battle analysis of the destroyed tanks revealed 94mm diameter penetrations through 76mm sloped armor. No Sherman gun could have produced that result from any angle. The first Allied intelligence report documenting the damage used the word undeniable. The Jagdpanther was the culmination of a philosophy that the Wehrmacht took years to articulate coherently. Not a general-purpose tank capable of multiple functions, but a pure tank destroyer optimized for a single function, built on the best chassis available. The decision to mount the 88mm PEC 43 L71 gun on the Panther chassis was formally adopted in October 1942, when the Heereswaffenamt, the Army's armament office, accepted the proposal from Daimler-Benz. The design eliminated the rotating turret of the conventional tank to install a low-profile fixed combat cabin with the gun protruding through an embrasure with 9 degrees of lateral travel and 15 degrees of elevation. This meant that to aim outside of this narrow arc, the entire vehicle had to be moved, requiring coordination between the driver and the commander, on which lives depended. The trade-off was total in firepower. The Pak-43 that armed the Jagdpanther was not the 88mm gun that had destroyed British tanks at Tobruk, nor the one used on the Tiger I. It was a substantially longer evolution, with a 6.3-meter barrel that generated a projectile speed of 1,000 meters per second for the PESGR 39/43 armor-piercing ammunition. At that speed, at 1,000 meters, it penetrated 190 millimeters of homogeneous armor. At 2 kilometers, where many enemy tanks hadn't even located the source of the fire, it penetrated 159 millimeters. The Soviet 1S-2, with its 120mm frontal armor, could be destroyed from distances where its own armament couldn't respond effectively. A Sherman, facing a well-positioned Jagdpanther on favorable terrain, was in a tactical dead-end situation. Production began in January 1944 at the MIAG plant in Brunswick. Allied bombings repeatedly interrupted the manufacturing pace. Attacks on Brunswick in October and November 1944 delayed the delivery of new units by several weeks. Despite this, 415 Jagdpanthers were completed between January 1944 and the end of the war, a number that reflected both the priority given to the vehicle by the High Command and the growing difficulties of German industry under sustained bombing. On the Eastern Front, records of destruction documented by units such as the Schwere Panzerjäger Regiment 656 were verified against Soviet records of losses. Lieutenant Alexander Kurov, commander of an IS-2 from the 7th Guard Tank Corps, left behind a Soviet archive testimony describing low-profile German vehicles opening fire from over 2 kilometers before he could determine their exact position. During the summer retreat of 1944 in Ukraine and Poland, Jagdpanthers in staggered defensive positions destroyed IS-2s and T-34/85s before the Soviet crews understood where the danger was coming from. The Wehrmacht never had enough Jagdpanthers. The divisions that needed them waited weeks for the promised allocation while operating with obsolete tank destroyers. Rivalries between the regular Wehrmacht and the Waffen-SS for the best equipment resulted in distributions that didn't always favor the units with the most operational experience. The Jagdpanther was exactly the weapon Germany needed in 1943 to compensate for its growing numerical inferiority. It arrived in 1944, when that inferiority had already reached a scale that quality tactical preparations, however exceptional, could not fully counter. It is the story of a precise instrument forged too late to determine the combat it would have decided. The flak panzer that calculated where the enemy aircraft would be when the shell arrived. In the spring of 1944, Allied aviation had turned any movement of German columns in broad daylight into a high-risk operation. The RAF Hawker Typhoon and the US AAF P-47 Thunderbolt attacked at low altitude with rockets and automatic cannons that could destroy anything from a half-track to a Panther in a single pass. The Soviet Ilyushin Il-2 did the same on the Eastern Front, with a regularity that Panzer Division commanders later described as the factor that most conditioned the pace of their operations in 1944 and 1945. The existing German anti-aircraft systems did not resolve the problem. The fixed-position 88mm flak guns were lethal to high-altitude bombers, but took hours to reposition. The Flakpanzer IV Wirbelwind and Ostwind offered acceptable mobility, but their gunners fought exposed in open turrets under the same fire they were supposed to counter. Placing a man in an open turret to shoot at a plane attacking at low altitude exposed him precisely to the fire for which the aircraft was optimized. The Flakpanzer Koalion was the most ambitious response to that requirement. Designed in 1944 on the Panther chassis, deliberately chosen to ensure it could keep up with the fastest armored units, it mounted a fully enclosed turret with 30mm of armor that protected the crew from the main fatal flaw of its predecessors. Inside the turret, two 37mm flak 103/38 automatic cannons in a twin mount could fire 500 rounds per minute in combined cadence, with an effective ceiling of 4,800 meters against aircraft flying at speeds below 600 kilometers per hour, which was the speed of the low-level attackers causing the damage. The fire control system included an analog computer to estimate the point of interception of the shell based on the target's speed and direction. Firing at a moving aircraft is not the same as aiming directly at the aircraft. One had to calculate where the plane would be when the shell arrived at that altitude, which required knowing the target's speed, course, and the shell's trajectory. The Coelian also added a stereoscopic rangefinder to measure distance more accurately than standard visual estimation systems. These capabilities were absent in the Wirbelwind and Ostwind and would have substantially improved the system's effectiveness against low-level attackers that had operated with relative impunity over the moving columns. 2 prototypes were built in the summer and fall of 1944. Tests revealed a promising system with solvable technical problems. The fire rate synchronization between the 2 guns and the ammunition feed system tended to fail under high temperatures. Engineers estimated that corrections would require weeks of additional development, not months. The High Command opted to postpone production until those problems were resolved, continuing with the Ostwind as a provisional solution. By the time the Coelian's issues could have been resolved, Allied bombings over German industry had reduced production capacity to levels that made it impossible to add another complex vehicle to the production line. In the Battle of the Bulge in December 1944, Allied low-level air attacks on the SS columns destroyed more vehicles than ground fire. The Ostwind did not prevent it. The Coelian was not there to try. Tiger II, the tank that no one could penetrate from the front. On August 9, 1944, in Saint-Thô, Normandy, Lieutenant Philippe Michard, commander of a Sherman Firefly from the Régiment Blindé Canadien de Maisonneuve, recorded in his diary the most accurate and disturbing description of the Tiger II in combat, 3 Fireflies against one of them. The first shot at 400 meters, it bounced off. The second shot, closer, bounced off. The third shot was at 200 meters, at an oblique angle on the rear side plate. That one penetrated, but we had already lost 2 of the 3 tanks. It wasn't a battle, it was an execution in reverse order. The Tiger II, the Königstiger, the King of Tigers, was born from a decision in January 1943. The OKH, disturbed by the first encounters with the Soviet YS-1 and aware that the IS-2 with its 122mm gun was under development, ordered the Heereswaffenamt to begin designing a successor to the Tiger I that would surpass everything the Soviets could deploy in 1944. The Henschel and Porsche companies submitted proposals. Henschel's, more conventional and mechanically more reliable, was selected. Ferdinand Porsche had bet on an electric transmission system, which turned out to be problematic and came late to the contest, though the Porsche-designed turret, already in advanced production, was used on the first 50 Tiger IIs before the Henschel turret, with its lower profile and better protection, became standard. The armor of the Tiger II was the reason for its existence. The front of the superstructure reached 150 mm sloped at 50 degrees, which provided ballistic protection equivalent to more than 230 mm of vertical steel. The sides of the hull were 80 mm. No Allied tank gun in service in 1944 could penetrate this front at normal combat distances. The Soviet YS-2 could achieve it at less than 500 meters with optimized APHE ammunition, but getting that angle and distance in actual combat depended on circumstances the Soviets could not guarantee. Combat records document instances where Tiger IIs received dozens of hits to the front without being penetrated, destroying enemy vehicles at distances where their targets couldn't effectively respond. The problem was the engine. The Maybach HL-230, which delivered 700 horsepower for the 44-ton Panther, now had to move 69.4 tons of steel. The resulting specific power was 10.1 horsepower per ton, the lower limit of what was technically acceptable for a combat vehicle. The maximum speed on roads was 41.5 kilometers per hour, but in real campaign conditions, it rarely exceeded 30 kilometers per hour sustained. The Olvar EG-40/12/16, a semi-automatic hydraulic transmission, was mechanically sophisticated and required a level of maintenance that many unit field workshops couldn't provide. Breakdowns on the move, especially on long transfers over difficult terrain, were a constant operational issue that commanders learned to incorporate into their availability calculations. Fuel consumption was the other limiting factor. On roads, the Tiger II consumed between 550 and 700 liters per 100 kilometers. In the field, consumption could triple. With Allied aviation systematically attacking German refining facilities and fuel depots since the summer of 1944, many units equipped with Tiger IIs received allocations that covered less than half of their operational needs. The Ardennes showed the clearest extreme of this limitation. SS Oberst Jochen Peiper's Kampfgruppe advanced with Tiger IIs and Panthers until they ran out of fuel at La Gleize, where they abandoned their vehicles intact because there was no way to move them. The Tiger II was a fortress on the ground, but fortresses need supply lines. A total of 489 Tiger IIs were produced between January 1944 and the end of the war. On the Eastern Front, the Schwer SS Panzerabteilung 501 accumulated one of the highest tank destruction records of the entire war during the winter battles of 1944 to 1945. On the Western Front, it was the vehicle most feared by Allied tank commanders, not for its numbers, but because every encounter produced disproportionate losses until they learned to flank it, isolate it, and wait for mechanical problems or fuel shortages to do the work that shells could not do head-on. Sd.Kfz 251, the nerve of the Blitzkrieg. On May 13, 1940, in the outskirts of Dinant, General Erwin Rommel observed from his Sd.Kfz 251/3 command vehicle as the first units of the 7th Panzer Division crossed the Meuse River under fire. What made the coordination Rommel oversaw possible at that moment, the speed of response, the ability to combine the movement of armored vehicles with the movement of the infantry on board, and the fire from supporting vehicles, was the communication system integrated into that vehicle, 3 different radios operating simultaneously. The FUG-8, 30 watts, for communications with the division headquarters. The FUG-7, 20 watts, for direct contact with close air support. The FUG-5 for local tactical communications with the vehicles in the sector. The Blitzkrieg was not just a tactical idea about speed and concentration. It was, to a large extent, an engineering problem of communications that the Sd.Kfz 251 solved. The Sonderkraftfahrzeug 251 was developed by Hanomag starting in 1938 as the standard transport vehicle for Panzer Grenadier divisions, the mechanized infantry that had to operate in close coordination with armored vehicles. The design adopted the half-track configuration, steering with conventional front wheels for road maneuverability, traction and weight support via the rear tracks with torsion springs for field capacity. This combination allowed it to cross terrain that rendered conventional trucks useless without reaching the weight and mechanical complexity of a fully tracked vehicle. It was the balance between what was needed on the road and what was needed when the road ended. The basic version, the S.D.Kf-Z251/1, carried 9 infantrymen plus crew in a semi-open rear compartment with 14.5mm armor. This armor was insufficient against infantry fire at close ranges, but effectively protected against artillery fragments and shrapnel, which represented the greatest danger to moving infantry in most combat. The open roof simplified quick disembarkation and allowed fire from the moving vehicle with the MG-34 or MG-42 machine gun mounted on the front of the compartment, a capability that conventional trucks could not provide. What made the Sd.Kfz 251 one of the most influential vehicles of the war was the proliferation of specialized variants developed on the same platform. The 251/9, known as Stummel, integrated a short 75mm howitzer for direct fire support to the disembarking infantry. The 251/16 carried 2 flamethrowers to flush out entrenched positions in dense vegetation or structures. The 251/17 mounted a 20mm Flak 38 anti-aircraft cannon on a rotating platform. The 251/20, developed in 1944 as part of the Sperber night combat system, carried a 600mm infrared spotlight that illuminated the battlefield with light invisible to the human eye, but detectable by the FG-1250 sights installed on modified Panthers. In field tests during the fall of 1944, the system allowed Panthers to detect targets at 200 meters in complete darkness. It was the first integrated night combat system in military history. The 251/3 deserves specific mention because its function was what multiplied the value of everything else. Configured as a command and communications vehicle, it was the central nerve of panzer operations during the campaigns in Poland, France, the Balkans, North Africa, and the Eastern Front. Heinz Guderian, who had intellectually designed the Blitzkrieg as a doctrine, coordinated Panzergruppe operations from vehicles of this type during the fall of France in 1940. The speed with which decisions were transmitted and executed was inseparable from the speed with which the 251/3 allowed them to be communicated. Total production reached 15,252 units in all variants between 1939 and 1945, making it the most produced half-track vehicle of the war. It was never enough to fully motorize all Panzergrenadier divisions. In practice, many divisions relied on conventional trucks for most of their infantry, reserving the 251 for the vanguard units where coordination with armored vehicles was most critical. Allied armies captured Sd.Kfz 251s in large numbers during the German retreat of 1944 and 1945, analyzed them, and their engineers came to conclusions that directly informed the development of the US M113 and the Soviet BTR-50 armored vehicles in the post-war period. The concept of mechanized infantry fighting in close coordination with armored vehicles from their own vehicles was not invented by the Wehrmacht, but it was the Wehrmacht that demonstrated, in the summer of 1940 and the years that followed, that it worked decisively. The Sd.Kfz 251 was the instrument of that demonstration. Pulverized coal on the wing, how the HO 229 came to stealth without looking for it. In April 1945, soldiers of the US Third Army entered the Gotha plant in Friedrichsroda and found something that no one knew how to classify. It wasn't a conventional aircraft, it was a wing, a single surface of wood and steel without a fuselage or tail, with two engines buried inside, and a pilot's cabin integrated into the central curvature. The engineers from the technical intelligence team who analyzed it over the following days sent a telegram to Washington with a single word of evaluation: extraordinary. The Horten Ho 229 was born from Reimar Horten's three-decade obsession with the pure flying wing. Since the 1930s, Reimar and his brother Walter built gliders, from the Ho 1 to the Ho 6, each demonstrating a central idea. Eliminating the fuselage and tail eliminated all the parasitic aerodynamic drag from these elements, radically improving efficiency. A conventional aircraft carries the drag of the fuselage, empennage and surface unions. A pure flying wing has none of that. The Luftwaffe bureaucracy listened to the Hortens with continued skepticism for years, until the urgency of 1944 changed the rules. Goering issued the specification known as the 3x1000, an aircraft capable of carrying 1,000 kilograms of bombs at 1,000 kilometers per hour with a range of 1,000 kilometers. No conventional design could meet this. The Horten design could, on paper. The HO 229V1, the first unpowered glider prototype, flew in March 1944 and demonstrated manageable characteristics for such a radical configuration. The HO 229V2, equipped with two Junkers Jumo 004B engines, made its first flight in December 1944. Test pilot Erwin Ziller reported speeds close to 800 kilometers per hour and overall performance that exceeded his expectations. In February 1945, Ziller died when one of the engines failed during a test, and the aircraft crashed near Oranienburg. He was the most qualified pilot on the program. There was neither time nor person to replace him. What neither Ziller nor the Hortens explicitly documented in terms of stealth design was that the wing structure incorporated properties that made it difficult to detect by radar. The core structure mixed pulverized coal with adhesive, a composite that partially absorbed centimeter radar waves. The wing's flat silhouette had an intrinsically reduced cross-section, and the engines, buried inside without external gondolas, did not generate the reflections that would give away conventional aircraft. Tests conducted by Northrop Grumman in 2008 with a replica confirmed that the HO 229 would have significantly reduced its detection on the Allied radar systems of the time, especially at low altitude. In 1944, German engineers did not have a formal science of radar stealth, but they had reached similar conclusions from a completely different angle. Goering ordered mass production under the name Gotha Go 229, with 40 pre-production units planned. Nothing materialized. The V3, nearly finished in Friedrichsroda, was the only survivor. It was transferred to the United States and is now at the Smithsonian Udvar Hazy Center, undergoing restoration. It is the only physical example of a design philosophy that the world would take 40 years to formally rediscover. Engineer Harold Luskin, who inspected the V3 in Friedrichsroda, wrote the first detailed report on the fuselage and its radar-absorbing properties. This report circulated in American aeronautical engineering circles during the 1950s, the same years when Northrop began exploring the flying wing for military use. The principles of the flying wing, with reduced radar signature that the B-2 Spirit engineers would investigate decades later, were the same ones Reimar Horten had partially implemented in a hangar in wartime Germany. The RAF captured He-162s intact and wrote that 6 more months would have changed everything. 69 days. That's the time that passed between the official approval of the He-162 program in September 1944 and the first flight of the prototype on December 6th of that year. No jet combat aircraft has gone from specification to flight in such a short time, before or after. The engineering achievement was real. The context that made it possible was one of a collapsing regime producing extraordinary technical results at the cost of a logic that no longer recognized the normal limits of caution or time. The Reich Ministry of Aviation had issued a specification in September 1944 that would have seemed impossible 2 years earlier: a jet fighter built mainly from wood and sheet aluminum, flyable by young men with minimal training and producible in mass numbers. Ernst Heinkel responded in 4 days with a design for a nearly circular fuselage with the WWII engine mounted in a dorsal gondola above the fuselage, an unusual configuration that avoided the complexity of integrating the engine inside and reduced the fire risk in case of engine failure. The wings, made from wood to conserve the strategic aluminum in short supply, had a moderate sweep. The standard armament was two 20mm MG 151/20 machine guns in the nose. Maximum speed, 840 km per hour at 6,000 meters, higher than the Me-262 at that altitude. Rate of climb, 23.5 meters per second, comparable with the best post-war fighters. The problems were severe, and some directly lethal. The glue used in the wooden wings proved unstable under extreme temperature and humidity. In the first months of operation, several cases of the leading edge of the wing detaching during high-speed flight caused fatal accidents before emergency structural modifications resolved the problem in later production units. The BMW-003 responded slowly to acceleration changes below 300 km per hour, a critical condition during the approach for landing when the plane is flying slowly and the pilot needs to adjust power with immediate precision. Several pilots died when, in the go-around maneuver, which is when a landing is aborted and the aircraft is intended to climb again, they increased the power too abruptly and the aircraft responded with violent, irrecoverable oscillations at low altitude. The Volksjäger program, the People's Fighter, envisioned the He-162 being flown by Hitler Youth members with a few hours of glider training. Luftwaffe pilots and instructors rejected the idea firmly, knowing that the He-162 required real skill to operate safely. The fantasy of an army of teenagers flying jet fighters with minimal training was the clearest measure of the disconnect between the regime's ideology and the physics of high-speed aircraft. 320 units were produced by the time the war ended, with another 800 in production at various plants. The primary operational unit, JG-1, began equipping with the aircraft in February 1945 and carried out a limited number of combat missions before the front collapsed. Confirmed aerial victories are scarce and debated. RAF intelligence teams that captured intact He-162s at airfields in northern Germany in May 1945 urgently sent their analyses. The aircraft had real problems, but also had obvious solutions. With 6 more months of development, it could have been a threat of a different nature. The program that Knipkamp proposed in 1942 to save German armored logistics. In 1942, when the Wehrmacht was still advancing on Stalingrad, engineer Heinrich Ernst Knipkamp argued before the Heereswaffenamt that the German armored system was on the verge of collapsing under the weight of its own complexity. Too many different platforms, too many incompatible spare parts between vehicles performing similar tasks, too many parallel manufacturing processes consuming scarce resources without producing economies of scale. A spare part from the Tiger I wouldn't fit in a Panther, which in turn didn't share components with the Panzer IV. Each armored division carried with it a multiplied spare parts logistics system. Knipkamp's solution was a family of standardized chassis from which multiple combat vehicles could be derived, simplifying manufacturing, logistics, and field maintenance. It was a technically sound argument that came 2 years too late, based on an industrial base that Allied strategic bombing was beginning to dismantle methodically. The E-100 was the maximum class of this family, projected to weigh between 130 and 140 tons. The Adler Works in Frankfurt was commissioned. The result was a vehicle 10.27 meters long and 4.48 meters wide. The front of the hull reached 200 millimeters of armor. The turret, designed for the KWK 44-128mm L-55 gun, the same one planned for the Maus, had 240 millimeters of armor on the front. No Allied anti-tank gun in service could penetrate this front. The peripheral track system, designed by Kneipkamp to distribute the exceptional weight, placed the wheels in an external position, simplifying field maintenance compared to the complex internal systems of the Panther and Tiger II. However, the resulting width exceeded most European bridges, which would have required specialized crossing engineering for almost any real strategic movement. The prototype was 40% completed when British troops of the 6th Commando Group found it in Haustenbeck near Paderborn in May 1945. The chassis and engine were installed. The turret and armament were not. Engineers from the Royal Armoured Corps who inspected it calculated that the Maybach HL 230-700 horsepower, identical to the 44-ton Panther, would generate only 5 horsepower per ton to move 140 tons. The Panther had 16 horsepower per ton. The Tiger II had 10.1. The E-100 would have had 5, half of the minimum operationally acceptable. The real maximum speed over rough terrain would not have exceeded 20 to 25 kilometers per hour. A breakdown in the transmission would have meant abandoning the vehicle. No recovery team could evacuate 140 tons with the available means in the frontline units. The prototype was transferred to the UK for technical study and then destroyed. What the E program inadvertently demonstrated was that the rationalization Kneipkamp proposed would have been a real necessity from 1942 onward, but it came when the industrial base could no longer respond. Hitler had rejected in 1942 and 1943 standardization proposals that could have improved the production of tens of thousands of lighter, more reliable and easier to maintain vehicles, instead prioritizing extreme armored projects that captured his attention. Kneipkamp's good technical idea never had the chance to prove whether it would have worked at scale. Panzer VIII Maus, the largest tank ever built. On December 24, 1943, at the Böblingen testing grounds, 188 tons of steel rolled for the first time on its own tracks. It was the Panzerkampfwagen 8 Maus, the largest combat tank ever built. The name Maus in German was ironically chosen in a way that Ferdinand Porsche, its creator, perhaps did not foresee. The Maus was the most modest of the monsters Porsche had designed, as the initial versions exceeded 200 tons. Hitler, who had commissioned the project in 1942 with the instruction to create an absolutely impenetrable vehicle capable of breaking any defensive position, received the news of the first rollout with satisfaction. Albert Speer, his Minister of Armaments, received it with the concern of someone who knew that the project consumed resources without providing an operational justification that the Maus could ever deliver. Its armor was unprecedented in any land vehicle. 200 millimeters on the front of the hull, 180 millimeters on the sides, 240 millimeters on the front of the turret. To put it in perspective, the Tiger II, the most protected German heavy tank in active service, had 150 millimeters on the front of the superstructure. The Maus had a third more, with an additional slant that multiplied the real ballistic protection. No Allied tank or anti-tank gun in service in 1944 could penetrate this front at any practical combat distance. The armament was equally extreme. The KWK 44-128mm L/55 gun could destroy any Allied tank at more than 3,500 meters, accompanied by a coaxial 75mm gun for secondary targets. With the Daimler-Benz MB 509 engine, producing 1,200 horsepower derived from the DB 603 aircraft engine, the Maus's specific power was 6.4 horsepower per ton. Maximum speed on the road, 20 kilometers per hour. On clay soil or ploughed fields, the vehicle sank under its own ground pressure before advancing significant distances. It could practically not cross any European bridge. For river crossings, a procedure was designed where the Maus would advance along the riverbed under a snorkel, while another Maus on the opposite bank would supply electrical power through an underwater cable to power the drive motors. This operation required hours of technical preparation for each crossing in a front where rivers were the main natural operational obstacle. Speer cancelled the series production in 1944. 2 prototypes were completed. When Soviet troops advanced on the Kummersdorf polygon in April 1945, the German personnel deliberately destroyed both to prevent their capture. The Soviets found the wreckage, combined the surviving parts from both prototypes, and rebuilt one example, which is now displayed at the Kubinka Tank Museum near Moscow. The Soviet technical analysis was definitive: insufficient tactical mobility for any real operation, unsustainable logistics in the field, total vulnerability to aviation. Every ton of steel in the Maus was a ton that didn't reach the Panthers and Jagdpanthers that Germany truly needed and which the Allies would have feared encountering. The Maus was the most expensive, literally the heaviest symbol of the disagreement between those who believed the war could be won with absolute invulnerability and those who knew it was lost due to the lack of thousands of well-built and well-maintained medium vehicles. The missile that traveled at 5,760 kilometers per hour and no system in the world could intercept. On September 8, 1944, at 1843, a thunderclap without warning shook the Chiswick area of London. There was no alarm, no sound of an approaching engine. The building simply exploded, killing 3 people and injuring 17. It was the first operational impact of a V-2, the first ballistic missile used as a weapon of war in history. It reached 5,760 kilometers per hour at the moment of impact, well above the speed of sound. The explosion arrived before any sound of something having been fired. There was no alarm system that could warn of its arrival because it came before news that it had been launched. The A4, the technical designation for the V-2, was the result of years of work by Wernher von Braun and his team at the Peenemünde Research Center on the island of Euston, where rocket experiments with liquid propellants had begun in 1937 under the supervision of General Walter Dornberger. The vehicle was 14 meters long, weighed 12.5 tons at launch, of which 8.8 tons were propellant, 3.9 tons of liquid oxygen and 3.96 tons of 75% ethyl alcohol. The engine burned this combination in 65 seconds, accelerating the missile from 0 to cutting speed at 88 kilometers altitude. The warhead carried 910 kilograms of amatol explosive. The probable circular error was 2 to 3 kilometers. It was not a precision weapon, but against a target the size of London or Antwerp, the imprecision was secondary to the effect of a threat that no one could intercept or predict. Production in the Nordhausen tunnels, the Mittelwerk excavated in the mountain to protect it from Allied bombing, cost at least 12,000 lives of prisoners from the Dora concentration camp doing forced labor. More died in manufacturing than in the launches. Albert Speer repeatedly questioned the cost-effectiveness of the program. The V-2 consumed more resources than any other German armament project during the war, including the nuclear program. Between September 1944 and the end of March 1945, 3,172 operational V-2s were launched. About 1,054 hit the London area, causing approximately 2,700 deaths and 6,500 serious injuries. Another 1,600 fell on Antwerp. The effect on civilian morale was real, but not decisive in any strategic sense. What the V-2 initiated transcends any measurement in terms of the 1944 to 1945 war. Von Braun and dozens of his engineers were moved to the United States under Operation Paperclip. The Soviets captured Peenemünde and the Mittelwerk, moved key engineers to the USSR and used the A4 as the basis for the R-1 rocket, the starting point for the R-7, the missile that launched Sputnik in 1957. The American Redstone, Jupiter and Saturn V rockets are also direct descendants of the technical line von Braun laid out in Peenemünde. 2 powers built their mutually assured destruction capacity based on the principles von Braun and Dornberger developed on a Baltic island between 1937 and 1944. And in July 1969, a rocket derived from those principles took the first humans to the moon. Sd.Kfz 251 and the Landwasserschlepper, mobility as doctrine. Before the American LVTP-7 existed, before the Soviet BTR-50, before modern armies standardized the amphibious combat vehicle as a standard element in their battle orders, the Wehrmacht developed the Landwasserschlepper. Built by Rheinmetall-Borsig since 1935, it was the first operational self-propelled heavy amphibious armored vehicle in any army in the world. The name describes the function straightforwardly. Amphibious land and water tractor, it was a tracked vehicle with a pontoon-shaped hull that provided inherent buoyancy, propelled in water by a rear propeller driven by the same land engine. The transition between land and water locomotion was direct. The vehicle entered the water, activated the propeller, and navigated. The Maybach HL 120 engine, producing 300 horsepower, provided 18 kilometers per hour on land and 12.5 on water. The 10 to 14.5 millimeter armor protected against small arms fire and light artillery shrapnel. The main capacity was towing. It could tow a pontoon barge loaded with up to 20 tons, enough for a full Panzer III or IV, or a heavy artillery piece with its tractor. Crossing wide rivers with heavy vehicles that would otherwise have needed engineering bridges that took hours to build under enemy fire. That was what the Landwasserschlepper made possible. Only 21 units were built, which reflects that it was a niche vehicle for specific river crossing scenarios. The Landwasserschlepper participated in crossing the Dnieper and other Soviet rivers during the Barbarossa operation in 1941, accelerating the pace of advance where conventional pontoons would have created bottlenecks. They were explicitly considered for the Seeluw operation, the planned invasion of Great Britain that never took place. In this hypothetical operation, they would have transported the first armored vehicles from the barges to the shore without the need for port facilities or solid sand beaches. The principles validated by the vehicle, amphibious hull, dual land-water propulsion, heavy load towing capacity, are the same principles that modern armies adopted as a standard decades later. The Wehrmacht had arrived earlier, but in too small numbers to be operationally significant, yet with a conceptual clarity that later developments would confirm. The Landwasserschlepper and the Sd.Kfz 251 share a fundamental trait that defines the best of German weapons thinking in the pre-war years and the early years of the conflict: mobility not as a characteristic of the individual vehicle, but as a function of the system. It was not about building the fastest or most protected vehicle, but the one that allowed infantry, armored units, command and logistical support to move together, coordinated, faster than the enemy could react. When that coordination worked, between 1939 and 1942, it produced results that rewrote military doctrine for the entire century. When the resources to sustain it ran out, the vehicles alone could not compensate for the difference. Landkreuzer P-1000 Ratte, the unmanageable tank. On December 24, 1943, at the Böblingen testing grounds, 188 tons of steel rolled for the first time on its own tracks. It was the Panzerkampfwagen 8 Maus, the largest combat tank ever built. The name, Maus in German, was ironically chosen in a way that Ferdinand Porsche, its creator, perhaps did not foresee. The Maus was the most modest of the monsters Porsche had designed, as the initial versions exceeded 200 tons. Hitler, who had commissioned the project in 1942 with the instruction to create an absolutely impenetrable vehicle capable of breaking any defensive position, received the news of the first rollout with satisfaction. Albert Speer, his Minister of Armaments, received it with the concern of someone who knew that the project consumed resources without providing an operational justification that the Maus could ever deliver. Its armor was unprecedented in any land vehicle: 200 mm on the front of the hull, 180 mm on the sides, 240 mm on the front of the turret. To put it in perspective, the Tiger II, the most protected German heavy tank in active service, had 150 mm on the front of the superstructure. The Maus had a third more, with an additional slant that multiplied the real ballistic protection. No Allied tank or anti-tank gun in service in 1944 could penetrate this front at any practical combat distance. The armament was equally extreme. The KWK 44 128mm L/55 gun could destroy any Allied tank at more than 3,500 meters, accompanied by a coaxial 75mm gun for secondary targets. With the Daimler-Benz MB 509 engine, producing 1,200 horsepower derived from the DB 603 aircraft engine, the Maus's specific power was 6.4 horsepower per ton. Maximum speed on the road, 20 kilometers per hour. On clay soil or ploughed fields, the vehicle sank under its own ground pressure before advancing significant distances. It could practically not cross any European bridge. For river crossings, a procedure was designed where the mouse would advance along the riverbed under a snorkel, while another mouse on the opposite bank would supply electrical power through an underwater cable to power the drive motors. This operation required hours of technical preparation for each crossing, in a front where rivers were the main natural operational obstacle. Speer cancelled the series production in 1944. 2 prototypes were completed. When Soviet troops advanced on the Kummersdorf polygon in April 1945, the German personnel deliberately destroyed both to prevent their capture. The Soviets found the wreckage, combined the surviving parts from both prototypes, and rebuilt one example, which is now displayed at the Kubinka Tank Museum near Moscow. The Soviet technical analysis was definitive: insufficient tactical mobility for any real operation, unsustainable logistics in the field, total vulnerability to aviation. Every ton of steel in the Maus was a ton that didn't reach the Panthers and Jagdpanthers that Germany truly needed and which the Allies would have feared encountering. The Maus was the most expensive, literally the heaviest symbol of the disagreement between those who believed the war could be won with absolute invulnerability and those who knew it was lost due to the lack of thousands of well-built and well-maintained medium vehicles.